Hello everyone, we are Team ENVE in a partnership with UConn School of Engineering and Leonard Engineering. We bring to you a project on the analysis and design of Meriden Rails to Trails.
I'm James Kennedy.
I'm Mackenzie Pius.
I'm Leo Abreu.
And I'm Jason Saltis. Together we make CASP Engineering.
During our project, we will go over the trail section and alignment plans, the new bridge and parking lot designs with their considered alternatives, the budget analysis of the materials used in the final design, and other considerations used when creating the plans. Here we have an analysis of existing conditions. The railroad tracks have been removed and we are left with a historical railbed, and the figure in the middle demonstrates the trail, which is approximately 1 mile long. At the top right, we start at a high school where some parking is available, and along the way we come across two bridges which will be replaced and redesigned, and towards the end of the trail there is a parking lot that will be designed for pedestrian use and emergency vehicles. Along the way, the flood analysis has been evaluated to determine where drainage should be located.
Our trail cross-section designs were developed based on FHA's Trail Access Design Guide and Surface Texture Technical Advisory and AASHTO's Guide for the Development of Bicycle Facilities. We included a typical trail design based on best practices for longevity, comfort, and accessibility, and an alternate with bioswales for drainage to minimize environmental impact from storm runoff. Our bridge alternates were designed according to ASCE's Steel Construction Guide, AASHTO's Bridge Design Specifications, and the DOT's Bridge Design Manual. The stone arch was designed for aesthetic appeal, the concrete beam bridge would last the longest, and the steel beam bridge would be the most cost-effective and the most environmentally friendly, as it would be comprised primarily of recycled material. The four parking lot alternates were designed according to Municipal Parking Design Standards and U.S. Access Board's Technical Guide for Parking Spaces. The different alternates focus on simplicity versus traffic control and efficiency versus aesthetics. The maximum capacity of the lot is less important, as the other end of the linear trail terminates in a public school parking lot, which can be used for trail access in the busiest anticipated times, such as after school hours or on weekends. The drainage designs considered include permeable pavers, catch basins, and a bioretention basin. While the former options would be less costly, the basin was designed to meet our focus of environmental friendliness, as it could treat contaminants in the runoff, and it's more inviting and an aesthetic natural design.
The grading and curvature were already satisfactory for the trail design. However, the geometry was still smoothed out just in case of any erosion that occurred previously to ensure that the trail is accessible to all users. The bioswales effectively manage stormwater runoff and offer little disruption from the natural landscape. Moving to the right side of the screen, we have visual representations of both the entire parking lot and the bioretention basin. The basin was ultimately chosen because of its effectiveness at treating not only the water volume, but any contaminants in the water as well. This choice also aligns the most with the environmental aesthetic and theme of the project as a whole. The parking lot layout is clearly centered around the basin and allows for maximal parking for trail users. The position of the handicap spaces in the parking lot also allow for direct access to the trail.
We ended up choosing the steel structure for the bridge, as it was very economic and could be constructed with ease. It would also be relatively environmentally friendly, as the steel beams would consist of mostly recycled steel. Although it is not as aesthetic as the stone arch, the bridge would mostly only be viewed from the walking trail, where the structure itself isn't very visible. SAP 2000 was used in combination with the LRFD Pedestrian Bridge Design Guide to select the proper beam sizes. The steel girders would be attached to a roller bearing at one end and a pin bearing at the other. These bearings are resting on abutments which are attached to the concrete wing walls. Over the roller bearing is a 1.5-inch expansion joint to allow for space for the beams to expand and contract.
Lastly, we have our final material costs. In the table provided are listed the materials that are expected to be used throughout the project. This was developed using the Connecticut DOT bid item list that was last updated on March 2020, along with the construction details of the plans for the bridge, the parking lot, and the trail itself.
We would also like to give a special thank you to Jim Erickson from Leonard Engineering and Dr. Zhang for spending the past 2 semesters guiding us through this project.